So hopefully this is more straightforward because this is going to be a long time that we've done this. Multiple times. Okay, analytic methods to find the absolute max and min of the function in the interval where they occur. Okay, so the first thing we're going to do is blah, blah, blah. Take the derivative. Okay, take the derivative. So we're going to go term by term. Derivative of e to the x? E to the x. Boom, there we go. Remember the chop chop guy?
I was actually picturing that one.
That's exactly. I try to find gifs to help you remember. I'm a visual person. What? You know? Oh, I'm sorry, I'm talking. Okay.
No, I don't remember.
We know. Okay, I gotta like rein myself back. I'm sorry. Derivative of negative x. Negative 1. Okay, yes, Spencer? Yeah, go lower. I don't care. Lower them all. I like darkness. Yes. Because it got dark really fast. Oh, I heard, yeah. Okay, so to find our critical points, aka like where our mix and min and max. Right, we set our derivative equals 0. Because think about it. Wherever you have a min or max, that's where your derivative is 0, because technically the slope would be a flat line at the top of a hill. Okay, so 0 undefined. This will never be undefined. So where is this equal to 0? Let's see. Where is, so you move 1 over. Where is e to the x equal to 1? At 0. Okay. So at, oh my god, is that looks okay. So ln both sides. ln 1 equals ln of e to the x. ln of e is just 1, so we say ln of 1 is x, aka 0. This is going to be our critical point. Okay, so we have an interesting point, and then we have our endpoints. So now here's the name of the game. You just got to plug these into the original function. So I'm going to say f of 0. That's our critical point, and then test both of our endpoints. This is probably the thing we missed the most. You have to plug it back into the original function. Okay, you gotta plug these values into the original, and you have to plug in the critical point you just found, not just the end values. Okay, you have to calculate the whole time. Make sure you're doing the math right by plugging in. Okay, so first one, we get e to the 0 minus 0, so that's just 1. E to the 1 minus 1. Oh wait, yeah, oops, negative 1. E to the negative 1. So this is just 1 over e minus 1. There's not much we can do about this. It's around like 1.368. No, negative. 1 over e minus 1.
No, is that plus 1? It's plus 1.
No, it's definitely a minus right here.
No, but it's
negative.
Oh my god, you got me. Oh lord. Okay, we got him. Okay, so this is 1 point.
We're all paying attention.
1.368. Yeah, I don't know. I thought I did it wrong on my answers. Is it salt? Is that what make you like have bad memories or whatever? Like not remembering signs all the time? I literally am messing up on negatives all of my classes. No, I'm like not eating any salt. I'm eating like really fresh food.
Maybe you need more salt.
Yeah, I gotta have more connections going to my brain.
Wait, salt has to do with math?
I don't know. Whatever memory. Okay, let's do the next one. E to the 1 minus 1. So this is just e minus 1, so it's 1.718. So I see that this is the smallest. This is our min. This is our biggest. No, it's not at all. This is our biggest. This is our max. Okay, so our max is f of 1 is equal to e minus 1. Our min, what?
Shouldn't we write 1 point?
This is exact, whatever. It's the exact same thing. F of 0 is just 1. It's the exact same thing. If you write 1.718, that's the same thing as saying 1 or e minus 1. Okay, how do you feel about this one? Perfect. Okay.
Whoa, wait a minute. Can you go up for 1 second?
Did you guys try number 2 already?
If I put for my max, instead of putting e minus 1, can I put the decimal it is?
It's the exact same thing. Yep. Alright, given the function on this interval, find each value of c. in the interval that satisfies the mean value theorem. Okay, so first,
What's the mean value?
I was about to. You don't have to ask them everything. Okay, so the mean value theorem says if you have a closed interval with ends that are included, and it has to be differentiable. So it's continuous, it's differentiable, and your endpoints are closed. You include your ends. Okay, so that's like the constraints. It has to be differentiable, you have to be able to take a derivative everywhere, it has to be continuous, and you have to include the endpoints. Okay, so just looking at the graph, okay, the thing I drew, that's clearly, let me draw it a little better. There.
Wait, can you say that one more time?
So it has to be continuous on the interval, has to be differentiable, so you have to take a derivative at any point in the interval, and your endpoints have to be defined.
So then,
those are like the constraints. This is what has to be true, and then what does it mean? If all these things are true, then what is the mean interval? Okay, so what that is, if I take the average rate of change, right? So this is literally the slope equation, right? Like y2 minus y1 over x2 minus 1. Literally the secant line, the average slope. That rate of change, what the mean interval says, is the average rate of change if we have a continuous and differentiable and closed interval. At least at one point, the instantaneous tangent will equal the average. So let me duplicate this. Okay, ready? Let's find the place where this is the... Oh, nope, that's close. Maybe a little more. Oh, okay, that's really close. Do you see what I mean? At this point, look right here, like this is the tangent for that point. But the tangent, remember, tangent only touches it once. It's like you're driving, you look at your speedometer at that instant. So one of your homework assignments was this truck driver was driving on this toll road, right? Let's say it was 100 miles and the speed limit was 50, but it took him less than 2 hours. So that means his average speed was above 50 miles an hour. Does that make sense? If he covered 100 miles an hour in less than 2 hours, that means he had to go faster than 50 miles an hour. So the reason if I was a police officer, I could give him a ticket is because there's no way if he was going the speed limit that he could cover this in less than 2 hours. So I know at least at one point he had to be going faster. Right? The mean value theorem, it says that the average rate of change from your beginning to end has to be the tangent at least one point. Okay, so what this means, I don't know if you understood the truck example. If I was going 100 miles and it only took me 50, I need a better number. If I'm going 150 miles and and the speed limit is 50 miles per hour, how fast should it take you? How long should it take you? 3 hours. Let's say I make it in 2 hours. Was I speeding?
yes.
How do you know?
Because your average is over.
Because my average is over the speed limit. So if my average is 75, that means at least at one point I would have to be going 75, right? Like I start at rest, I speed up, and then I slow back down. At least at one point I would be having to go the average. So according to our graph, at least at one point, right, the slope, the tangent line, at least at one point has to be equal to the average. That's what it says. Okay, so that was...
You would also be going over.
Well, yeah.
Because in order to balance to get 75, you have to...
Yeah, exactly. That's the average. That means I probably was going 100 at some point. I don't drive like that. I'm not crazy. Okay. But old grandma was. That was crazy. 120 miles an hour on the 118. Okay. Given the function f of x is equal to ln of x plus 2. This I handed out yesterday. It's just extra problems. It's not homework. There's 4 homework assignments, 4.4, 4.6, and 2 reviews from the book. Okay, so issue, ln of x. Do we know what ln of x looks like? So literally all of this thing that we're doing right now should hopefully take you 5 seconds, right? It's not meant to be like a full review of mean value theorem and have to think it through. Like you should know, okay, ready? This is how you approach a problem. ln of x roughly looks like this. But ln of x plus 2 means I shifted over by 2. So it means my vertical asymptote is at x equals -2. Issue, I'm not defined for less than -2. So if my interval was from -5 to 5, nope, can't satisfy mean value theorem. If you have places that's not defined, not continuous, non-differentiable on your interval, you just say no. You can't apply mean value theorem and you move on with your life. That's it. But here, We're going from -1 to e. So -1 is about right here. And e is probably something right here. So this is the interval we're going. Can we apply mean value theorem? Yeah, because I just showed you the interval, right? It's continuous between these points. It's differentiable between these points, and my endpoints are defined. Okay, I can apply mean value theorem. That means the average slope between my 2 points has to equal like the instantaneous, the derivative at a single point. So the way we do this, let me write out the equation. Right, we have f prime of c is equal to f of b minus f of a over b minus a. So hopefully this part takes you 5 seconds to do. Right?
And this formula is something that you memorize.
I mean, yeah, it's just like the slope equation on the right side, right? y2 minus y1 over x2 minus x1. It's just slope. Do you recognize that? Like f of b is just your y, your second y value. Okay, so what I'm trying to do is set the left side equal to the right side. So first, let's find what the derivative is. So if f of x is ln of x plus 2, what is the derivative going to be?
1 over x.
Yeah. So if I say, okay, let's plug in c, what's f prime of c? 1 over c plus 2. Yeah, that's it. So we're going to plug it in over here to the right side. I'm sorry, the left side. I have 1 over c plus 2. What about my right side? What's my a and my b?
-1 and e.
Yeah. So this is my a, this is my b. So I have f of e minus f of -1 over e minus a -1. So that's literally just going to be e minus a -1 plus 1. Okay, so I'm trying to show you every step, showing you how we have the left side equal to the right side and we solve for c. F of e, plug in e. So I have ln of e plus 2 minus ln of -1 plus 2 all over e plus 1. Well, -1 plus 2 is just 1. ln of 1 is 0. So I'll have 1 over c plus 2 is equal to ln of e plus 2 over e plus 1. I'm going to pause here and make sure we're good.
Actually, where did the plus 2 go?
Plus
I
2.
see. Okay, so let's say for the ln, parentheses, -1 plus 2.
Yeah, so -1 plus 2 is 1. ln of 1 is 0.
So 0 plus 2 is 2.
No.
Okay.
So -1
Yes.
plus 2.
Oh, you did that first,
It's
and then
1.
it was 1.
And then ln of 1 is 0.
0.
Where
Okay.
does the plus 2 come from? Comes from the c plus 2?
So plugging in my x and -1.
Okay.
So I was trying to show you plugging into my function.
Yeah.
Yes.
When you start, when you crossed out the ln and -1, did you just do some thing with...
I didn't cross out ln of -1. I crossed out this whole thing because that's equal to 0.
Okay.
Was that your question? Because Okay. All right, so we have to solve for c. We're trying to find the magic value where the derivative at that point will be the same slope as the average. So I just have to solve. Yay. Okay, so if you plug into your calculator the right side, you get 1 over c plus 2. Plug into your calculator the right side, you'll get 0.417. Little tricky trick. You can, if you flip both sides, makes it easier to solve for c. So I'll have c plus 2 is equal to 1 over 0.417. Subtract 2, and we see c is 0.398. So the hard part about this question is just making sure you set it up correctly, and then it's the algebra, getting c by itself. So I take the derivative. Yeah. So the average is roughly going to be the same as that guy right here. 0.398. Cool.
Wait, how's not deeply negative?
No, of course my drawing's not exactly to scale. My drawing's not to scale.
Wait, but how is it 1 over 0.417 minus 2.
Because if you have 1 over a half, that's 2. Because you're dividing by 0.4. Dividing by a number smaller than 1 makes the number overall bigger. Yeah. So if I was dividing by 0.5, it'd be 2. Since I'm dividing by something less than 0.5, the actual thing would be over 2.
I see.
And we don't have to write it as like x and y. We can just write c equal.
Right, because we're looking for the value. Like which x value. We don't want to say, oh, x is equal to this, because x is like our horizontal values. I want to know which one. So c is the magic x value where the derivative is equal to.
And then let's say like when we're doing this, we don't like think of the graph and we don't like think of it satisfies the mean value theorem. If we do it, will we get like no solution or something like that? Or is it just like
You could probably get a value. Weirdly, yeah.
Is it possible to have multiple values of c?
No. Well, yes,
Why
actually.
does it say find
Yes, you
each
can.
value of c?
There could be more than one. Yeah. Because imagine that I had a graph like this. I have my endpoint, the slope. There could be multiple points. Right, there could be a right here, right here, right here, right here, right? There could be like 4. That's satisfied. Cool. All right, let's keep going. Number 3, use anecdote, blah, blah, blah. Okay. You guys want to try this out yourself first?
Yeah.
Okay. Give it a shot. I don't know, I'll give you like a solid 20 seconds, right? So work. Yeah, I mean, the answers to these have been on mine for a while. So I'm going to get through as much as possible. Does anyone need an extra copy of the practice test?
I'm lactose.
Good work, Mr. Mendy.
No, it's not a vocab test today.
Oh.
Oh my god, yeah, I hate the words are the most.
You guys want to close your computers? I have up
I
here.
have the answers on.
We're going over it. We're going over it. You show your computer. I don't allow people to use computers in here unless it's for Alex, and we're done with the lesson.
It's like emotional.
I hear you, but also, you know.
Okay, I understand that. What if something is 0 when you
What do you mean?
you want me to help you? Draw the number line and plug it in, and we plug it into the original or into the derivative?
So you get the positive, negative by plugging into the derivative, and then those you draw up and down.
If I get 0. Oh, it's
I know.
I have a question. How do you know
I'm trying to see how you got that for the first derivative. I don't know what you plugged in.
No, that's what I find the local. I plugged in -2. Oh, okay, so that's what I did.
Okay.
I have a question. How do you know whether to do open bracket or closed bracket? Because
Intervals, you don't have closed brackets.
so intervals are gonna be like hard brackets. I've had enough.
I should have him sit just near me so I can just like make sure he's not doing what he's supposed to. No music. No music. Okay. First thing I have to do. Take Ty. What? Why? Okay. First thing we do. What's the first thing we do?
Prime. Derivative.
Take the derivative, right? We find the prime. Okay. F prime of x is negative 6x squared plus 6x plus 12. What?
It's like.
Okay. Cool, I found a derivative, but now guess what? There's a common factor I can pull out. Pull out a -6. That way I have a positive in front of my x squared.
Test just be these kind of things.
Yeah, of course. That's such a good idea.
Yeah.
No, why? No, what?
So excited.
Exact same thing. Wait, so are intervals always going to be closed? Like
Open. We're always,
parentheses?
yes.
Oh, so there's no brackets on these whatsoever?
Correct.
There's no brackets?
Intervals, because we don't want to include the point at which I'm switching from increasing to decreasing. That's like the neutral party. It's like a judge.
God bless you. Okay.
Right?
I know I shouldn't have been looking on my computer, but there were brackets on there.
Yeah, I know. I didn't make those solutions.
Ooh, tea. Oh.
What? I was saving time because I just gave you the same practice test as what they used last year. I'm trying to work smarter, not harder, Hannah.
I like that.
I want to use my time to, like, I don't know, grade your quizzes and tests.
You should be.
Also, I'm training for like an hour and a half a day, and I don't have time to make the solutions of certain.
That's awesome. And you should.
All right, x minus 2, x plus 1. So we have two solutions to a negative 1. These are going to be our critical points. So, you ready? Here's the deal. So I feel like you guys can do the left side fine. Here's the issue. Here's where we mess up. Language.
Her jeans are so cute.
They are cute, but we're focusing, right? Think about Monday, right? Future you doesn't want to cry. Future you wants an A. Future you really wants to, like, take this test and walk out.
Okay, yes.
Okay. So, like, whenever I'm going through something I feel overwhelmed, I'm like, you know what? In like 2 days, I'll be so happy I just work through this instead of let it pile up. Think about that. Be a friend to yourself. Be a homie. I feel you. It is what it is, you know? We just gotta go through it. Alright, so we're gonna be plugging into the first derivative, aka this guy right here. If I plug in 0, I'll have a negative times a positive. So guess what this is gonna be? It'll be, wait, hold on.
Wait a minute. What? I got -2.
It should be negative.
No, I got negative.
I got -2 and 1.
It should be negative.
Oh,
I got negative.
sorry, positive. I was trying to put a number right here.
Wait, no, it should be negative.
No, it's positive.
What?
I was trying to put a number right here. I forgot my bad. So it's positive. Negative times a positive. Because if I plug in 0, I have a negative.
Oh.
0 minus 2 is negative times positive.
Are you talking about the left side?
That's what I originally was trying to do, and then I realized I did the middle. Ah, okay. Ready? Rule of multiplicity. Rule of multiplicity. Okay, cool. So that means my function is going to be going down, up, and down, which means I will have a min here. I'll have a max here. And it's very easy to tell where we're increasing. So it means we're going up. Decreasing is going down. So the only place we're increasing is from -1 to 2. I see your hand. Just a moment. And decreasing is where we're going down. So that's part B. So from -infinity to -1, union to infinity. Yes.
So when I was plugging in like the values to see if it was positive or negative for the number line, I did it into -6x squared plus 6x plus 12.
Okay, and you'll get the same answers.
So I can do that.
Yeah,
I did
you get the
the
exact
same
same
answer, but
answers.
I didn't know if it was like twice.
It's still the first derivative, as long as you're plugging into the first derivative.
Not that one.
Right. So we get the plus and minus by plugging into the first derivative, and then that slope tells us if we're increasing or decreasing.
And then when do we plug stuff into the original one?
When I'm trying to find what the values of the min and max are.
Okay.
So I see I have a max at 2, but what is the actual max value? Then we'll plug into it, yeah. Okay. Increasing, decreasing, check. Why don't we knock out E and F while we're here, right? E is local max, F is local min. So we might as well. So we know we have a min at -1. So I plug -1 into the original equation. I have, let's see, 2 plus 3 minus 12 plus 1. So this is -6. Which one's the min? This one. Okay. So f of -1 is -6. And then max. So right, you don't necessarily have to like do these in order since we're here, talking about min and max. Let's just knock it out. Max is at, max is, okay, max is part E. So max is at 2, I plug it in. I have 8, -16 for plus 12, plus 24, plus 1, 36, 37, 21? No. Yeah, 21. Okay. F of 2 is 21. It's a good movie. You should watch it.
What? 21?
Yeah.
Okay.
Fun fact. Literally only the bridge scene. The rest of it, I think, was filmed at Harvard. Or UCLA.
No.
MIT wouldn't let them on campus.
What's a famous actor that's on it?
Jim. Jim.
He's arrested for.
Jim Gaffigan. No, that's not his name. But who's the guy? He was in Across the Universe. Whatever. All right. I'm gonna continue on.
The character in House of Cards.
I don't know. Oh yeah.
It's him. That's who it is.
Oh, that's not who I was talking about.
That's who I'm talking about.
Because that guy's a sexual offender. No, I'm.
He's a big actor in that movie.
Yeah, I know.
Who's a sexual offender?
Jim?
Spade.
Yeah,
Kevin Spade?
Kevin Spacey.
Oh,
Kevin Spacey.
Spacey. See, all together it would be a good team. Okay, so where are we concave up and concave down? How do you find concavity? Second derivative. Okay.
I love that.
It's the second derivative. Okay. So, I'm going to take this -12x plus 6. So I can pull out -6. So this is 2x minus 1. So that means x is 1/2. This is a sad. Wait, is that confusing? Are we good about this?
I got x equals 2.
Nope. You add 1 to the other side and you just divide by 2.
Why do I have to take out -6?
Or you don't. Take this, set it equal to 0. -12x plus 6 equals 0. So -12x equals -6. X equals -6 over -12. That's 1/2.
Oh.
Okay. Okay. So concavity. All I need to do is pick a number. I'm gonna pick 0. Putting in 0 is positive, and over here is negative. That means concavity looks like this. If you're happy and you're positive, you're smiling, right? If you're negative, you're frowning, you're sad. Okay, cool. So where we concave up is C, so everywhere until 1/2, negative infinity to 1/2, and that means concave down is 1/2 to infinity. And then G, local points, okay, points of inflection. So I literally have to take 1/2 and plug it into the equation.
But the original.
The original. Okay. I want to find the actual point. I have the x, we want to find the y, so you have to take f of 1/2.
You have to take your value from your second derivative and plug it into your original.
Take your x value, because it is a point of concavity. We're changing from concave up to concave down, and the second derivative is 0 at 1/2. Has to match both of those things.
I forgot.
A point of inflection has to be where the second derivative is 0, and you have to be switching concavity. Same way with a critical point, you have to have the first derivative be 0 and switch from up to down, right? Okay, so you plug it in, because we're trying to find the point, like where is the point of inflection? The x comma y. Yep, trying to find the x comma y. Okay, cool. Yes.
Which equation did you put the 1/2 into?
Into the original function.
Yeah.
Because we're trying to find an x comma y coordinate, the point of inflection on our original graph. Okay, next problem. We're going to use, so 4, 5, and 6 all deal with the exact same equation. Use the derivative. Use the derivative to find where y has local max and local min. Oh my gosh, I literally gave you the first derivative. Woo. So.
Would it be fair to say that the majority of this test is this stuff rather than things from 4.6? Just wait, we still have 5 more pages in this review packet. Okay, so I don't know.
This is 4.4. That is it. That is the
This is how
title.
long our real life test is gonna be.
That is the title. Okay, so here are my critical points at -1 and 3. I can plug in 0. If I plug in 0, I get negative, positive, negative, so I'll be positive. What? Negative? 0 plus 1 is positive, 0 minus 3 is negative. I just want the sign, I don't care the real numbers. And then, since this is clearly a polynomial, because it's not rational, we're not anything in a fraction, so we know it's a polynomial. If I multiply it out, it'll be, a quadratic. I know what this looks like. It's going to be rule of multiplicity.
Do we have to unprime it?
What?
No.
That's the next chapter, is how to unprime. I give you something and you anti-differentiate it.
No
But so
way.
for this, remember?
Integrals. What?
Remember when in the last problems, like when you do like f of -1 or f of 3, you put it in the original?
Yeah.
So would we just put it in the prime since that's what we're together? Do you know what I mean?
Well, we don't. It's not asking us to do that. Like, this is only one of the x coordinate, not the xy.
Oh.
Okay. Okay. So this means our function's going down, going up, going down.
Mr. Brian, did you have 2 points that had the same?
What's going on right now?
Mr. Brian?
Maybe I'm confused. Like, I thought we had a test Monday and we're going through a practice test. I'll wait. I'll wait. You have a question? Are we good? I wasn't sure if you guys are on topic or not. Okay, so before I went on, I want to make sure you heard. So Maya had a good question. Like, what if? He goes to talk. Maya had a good question. What if I asked you to find the point of inflection, not the x coordinate, but the point? Like, you wouldn't be able to right now because I haven't taught you how to find the equation, the original function from the first derivative.
With the point of inflection?
Yes.
Isn't that just from the second derivative?
That's the x is from the second derivative. Then you have to find the y. To find the y, you have to plug into the original function. We don't have the original function. Okay.
Yeah,
So
then we can't find the
So make sure you follow the directions. If I only want the x coordinate, write it. But if I'm wanting the point of inflection or the, how did I word it up here? The local max and min, you literally have to tell me the x, y coordinates.
But are you asking for local maximum?
Used to find where that's the x value. I didn't say what the max and min was, but where the location is the x value.
Oh, so it would just be x equals.
Yeah, exactly. So I have a min here and a max. Yes, Spencer?
Should the min and max be at the same point?
No. If you have because then it would, this is what your graph would look like right here, because you're not actually changing to decreasing. Literally, to have a max, you have to go from increasing to decreasing.
Then this doesn't have a maximum and minimum.
It does.
It's 0.
Yeah.
That's why I was asking.
The derivative, the first derivative is 0 at -1 and 3. But the actual function will have a min and max at -1 and 3.
We don't know that.
Yeah, we do. Because my slope is going from going down to going up. When you go down to up, that's a valley. That's a minimum. Notice I changed colors. Green is the first derivative. It's telling me the sign of the first derivative.
You plug it back in.
Well, because you're plugging into the first derivative function. You have to be plugging into the original function to find what the min and max value would be. Exactly. That's why I'm not asking you what the min and max are. I'm asking you where. Where is the location? Where is the x value? So, A is the local max. We know we have a max at 3, so it's at x equals 3. The local min is at x equals -1. Notice I didn't ask what value the min and max were. Okay. Notice I didn't ask you what they were because you don't have the original function to plug into. Hopefully by the end of the next chapter, I could give you a problem like that because we're learning how to anti-differentiate. So taking the derivative, you will take the antiderivative. Okay.
What? Question.
That's the next chapter. Yep, and we are going through it in chapter 6 before the seniors leave. Okay.
So,
I think I'm excited.
Would you solve this in person? Would you then just multiply all out there?
He has a question. You may have the exact. If you ask me the same dang thing, I will not answer it. I'm not going to answer your dang questions if you're not listening the first time it's asked. Right? I know. I'm a teacher. I need to answer all your questions, but it's your fault if you're not paying attention. Okay.
The question was that it would just be that you just do the you just do the derivative in reverse.
Are you asking how to do it?
Yeah.
No, that's the next chapter. I'm not going to discuss it now. All right, find the x-coordinate of the point of inflection. So we have the first derivative, right? The first derivative from up above is -2 times, okay, let's FOIL x plus 1 times x minus 3.
X squared minus 2x minus 3.
Cool. How did you know it was -2 in the middle? Did you have -3 plus 1?
3 minus 1.
Yeah, they add to -2 and multiply -3. And then take that -2 and distribute it out. -2x squared plus 4x plus 6. Okay, now we can take the second derivative. I'll pick a different color. Now we take the second derivative. -4x plus 4. So if I want to know where is my point of inflection, I mean, theoretically, right, I have to see which x value is my second derivative going to be equal to 0 if I plug it in. Like, which x value makes my second derivative equal to 0? So x equals 1. So, two things are required to be a point of inflection. The second derivative has to equal 0 at that x value, and you have to have a change of concavity. So if I plug in 0 into here, it's positive. If I plug in like 2, that's negative. Okay, so I do have a change of concavity. This is definitely a point of inflection. We're good. All right, this is at x equals 1. So the next part is to sketch a possible graph of y, the original function. We don't know what the original function is, but we do know roughly what the graph will look like. So the first derivative is like a quadratic. What do you think the original function is going to be? So notice, first derivative is a quadratic, second derivative is linear. So if I like go in reverse, I go from linear to quadratic to?
Linear.
Keep going up. First power, second power? Third power. So it's going to be a cubic function. Okay, so we know what it's going to look like. It's going to be a cubic function.
Wait, whoa, really?
No. Also, this literally tells you right here, I go down, then up, then down. Guess what I just drew with my red? It's a cubic function. Cool. Okay. So we know we know our derivative should be 0, right? It should be flat. I should have a min at -1. So I'll have -1 maybe be like right here. Or so.
You can do any y value.
You can do any y value, but I have to make sure the rough sketch is going to be clear. So I know I'm going to be decreasing.
Is it fine if we do it like under?
Yeah.
We do a y value.
So it's be 0 here. At 3, I have to have so at 3, I'll have 3 be like, I don't know, up here. 3, the slope has to be 0. So I know it has to be roughly 0 and be going down. I know this has to be like the bottom of has to be a min at -1, so it's got to be like a bowl.
But you can pick any y for that?
Yes, but it has to be matching. Like I have to have it be concave up. I have to have it be decreasing and then have a slope of 0 and then start to increase. So at what point am I switching from bowl up to bowl down?
1.
At 1. Okay, so at 1 right here, I should be switching from bowl up to bowl down. So maybe I should move this down a little bit so it's a little easier for myself. And maybe I'll move it down a little bit. That's also fine. This is why you have pencils. So I'm scooping up and then I start scooping like across. Bowl like this, and then it's kind of like when you're drawing sine waves. Like this is the point where you're switching from concave up to concave down. This is roughly what it looks like. So, if you look at the first derivative line chart at the top, right? At the top of your paper, it's going to match. We are decreasing until -1. And then we are increasing till 3. And then decreasing for the rest of the x. Notice our slope, right? If you're looking at the first derivative, f of x, f prime, 0 at -1 and 3. And the second derivative says, okay, I should be changing from concave up to concave down at x equals 1. Right? I'll be switching from scooping up to scooping down. So it's kind of like when you're drawing a sine or cosine, you know when you're like drawing sine and like you have the bottom scoop and then you have to change to do the upper part? Like you're literally switching, it's almost like an S looking thing. Okay, no. Cool. Maybe it's just me. You know, when you're drawing sine and cosine? No, whatever. Okay.
I know.
0, max, 0, min, 0. Like when I go to fill it out, I know that this is going to be coming up, and then I have to switch to like bowl down. You know, this point that I'm switching, like this is the shape, that's a change of concavity. Coming from bowl down to bowl up, like at that point. It's like this shape right here where I'm switching from the facing up one to the facing down. Okay. Number 7. Well, I think, did we knock this one out? Nah, not with 3 minutes. If we have questions, we won't be able to. We can do number 8. Number 8 is pretty short. Given the function, find y prime. What do I need to use for part A? Product rule. So I'm going to have u be x squared and v be e to the negative x. So if u is x squared, u prime is just 2x. V is e to the negative x. So v prime is negative e to the negative x. Because derivative of e to the x is just e to the x, and then derivative of whatever the exponent was. Okay. Product rule. So y prime, negative x squared e to the negative x.
Isn't it negative x minus 1?
Yeah, that's why.
What? No.
Why
You don't.
have to subtract 1?
That's if you had x to the, like, 2, you subtract 1 from the 2. If you had x to the 2, you'd subtract 1 up here and bring the 2 down. But since it's e to the x derivative is e to the x. If you have e to the x squared, it's going to be e to the x times the derivative of x squared is times 2x. Times the derivative of what the exponent was. So this is the rule for e to the x. Okay. Okay, so I have u times v prime times u prime v. And I could simplify this a little bit. I could pull out e to the negative x. So that way I have negative x squared plus 2x. So that is y prime. So that's part A.
We don't have to distribute it.
No, I mean I pulled out what I needed to. It just anti-distributed, factored out in e to the negative x. Part B, the interval where we're increasing, decreasing. You just, like, e to the negative x, it will never equal 0, right? E to the negative x never touches the x-axis. So therefore the y value will never equal 0, right? So I just only have to set the negative x squared plus 2x equal to 0. Pull out an x. So I have 2 minus x. So I see the 2 critical points are 0 and 2. And then to figure out, up or down, I just have to think about it. Well, I know what negative x squared looks like. Negative x squared points down. So I know at the ends it's going to be going down. And it'll be increasing in the middle. Okay, or you could plug in like 1. Right? If you plug in 1, negative 1 plus 2 is 1. And then rules of multiplicity. So, you would be increasing from 0 to 2. And decreasing from negative infinity to 0. And then 2 to infinity. That one's a pretty short one. What questions do you guys